few administrivia items. A lot of people ask, we are posting the videos, we are posting the slides probably later this week. Check out the blog at anyscale.com for details. We'll also, of course, tweet at these links. We have a lot of questions, and I'm going to try to get through as many as I can in the short time we have left, but bear with us if we don't get to your question. One that I have for both of you is, as researchers who are looking at the future as well as thinking about pragmatics of today, what are some things that are on your horizon that you're really excited about that you think the audience should be aware of? This is for both of you.
I'll let you take that one, Jan.
I'm sure quantum computing is right up there for you, Jan.
No, I think that, look, when we are talking about, and it looks like inevitable, like we are talking about distributed computing becomes a norm. This raises a huge number of research challenges, and which we would need to address. It's obviously, it's both on the system side, how you are going to build these general frameworks. As we know, building something more general is more difficult. It's not only to build something general, but you need to build something extensible, like you can support not only the application today, but the system should be flexible enough, accessible enough to support future application. One great example of a success story in this sense, is the internet, right? The internet, people didn't envision early on when they built it that we are going to conduct all our businesses from home or using video conferences. Actually, they didn't, even when people were talking about the video conference applications, they thought that not the internet in the current form we now is going to be the solution, but they started to develop new architectures and like ATM, many elders remember about this. And they invested billions of dollars into that technology, which ultimately failed. So I think that's a big challenge, how you are going to build something general, fast, and evolvable, right? I think the other thing is about, when you are talking about doing distributed computing, writing distributed programs and so forth is hard. So we can make it easy for building by building higher level libraries, and like we are building like reinforcement learning and libraries and hyperparameter tuning and so forth. But I can envision that we are going to also build tools like will at least assist the developers in parallelizing, distributing their sequential code, which is again another holy grail of programming, at least for the first 40, 50 years. So I think we are going to see a lot of progress there as well. And look, specialized hardware is here to stay. So integrating this hardware and abstracting it away in the applications, it will be a challenge which will only grow. You'll see more and more heterogeneous compute out there.
Yes, thank you. Maybe a question for you, Mike. Do you see causality becoming a larger focus of ML in the future?
Yeah, I mean, the short answer is yes. Longer answer is causality is a 100-year topic. It started with Neyman in the 1930s, talking about counterfactuals and outcomes in different branches, and sort of people who do medical decision making talk about causality all the time. Right? If you find a drug that's just correlated with some outcome, it's not enough. It's got to cause the right outcome. So there's a huge literature on causal inference, and it's just kind of been neglected. Machine learning people have focused on certain topics and gotten really good at digging into them, going quite far, and they just haven't paid much attention to some other topics in inference. And so finally, people start to realize causality is important. Now, from my point of view, to focus on these decision-making things, it's kind of a necessary but not sufficient condition for decision-making. If I don't know the variable that's causal for some outcome, I'm not going to affect that outcome. I would like to have like in a control system, an effect on some outcome, And I can't just find variables that are correlated with that outcome, right? I have to find ones which are causal. So I have to kind of run a causal inference thing first, and then I can start doing decision making and planning. So a lot of the classical literature assumed you knew those variables a priori and you could do the planning or the decision making. But the bigger problem definitely brings causal inference in as part of it.
So the three of us have been around a little while, I think I can safely say, and we've seen a lot of things come and go. There's a lot of things that are hot and topical now. Are there things that we've kind of put aside that, proven methods, techniques, whatever in the past that we really should be bringing back to the fore? Any thoughts about that?
From my point of view, machine learning is not a new field. It's drawing from others, and it's what it is, kind of an integrative discipline. It takes ideas from left, right, and center, from optimization, from control, from pattern recognition, from statistics, from distributed systems and all, and brings them together in all a big soup and problem solves. Tries to look at a particular problem. Maybe it's a recommendation system. Maybe it's, detection of some anomaly or whatever. And it's really the kind of integrative discipline of bringing all those things together. So in some sense, I think our discipline's been good at that, is making sure that old ideas are still kind of in the picture, that they're being used. But we haven't really, the scope of our problems we've been solving have been so limited to, is there a bunny in the image kind of thing? Applications to surveillance and all that. And maybe a little bit of natural language processing, but not even much, not much real dialogue and so on. So I really mostly want to encourage people to think out of this box of just pattern recognition and classification and think about the broader problems. Just one example of a problem that you'll face when you start to do that is the need for simulators. So people have already realized that for cars and robots and all, but that's going to become more and more the case. If I develop some decision-making algorithm for logistics chains or something, or supply chains, I got to try it out. And it's going to be expensive to try it out in the real world. So I've got to have pretty decent simulators where I can start trying it out. I think there'll be a whole wave of people working on that. Real good simulators for interesting domains, and not just a single robot, but for real world medical systems or real world commerce and so on. A lot of companies already have these things inside, but they don't really use them in this way. So part of Ray is also allows you to integrate in simulators. That's kind of the notion of an actor, and then take the output of that to drive the search that does something like reinforcement learning. So a platform that supports integrated decision-making and simulation and data, that's very much on the agenda.
Yeah, so I think that this workload convergence and building systems like Ray to support all these workloads brings also together a lot of techniques which span, the last 40 years. So for instance, one example is, say, the group communication and MPI. This was at the core of the HPC, high performance computing. However, over the past 20 years and so forth, I don't think we teach the students too much about that, because we are focusing on big data and obviously internet and things like that, which they have quite a bit of different patterns. However, with the emergence of distributed training and deep learning, people went back on to that, and actually quite a few systems which are doing distributed training are built on top of MPI, for instance like Horovod. And we are going to, and like for instance today in Ray, we are making, it's a lot of effort to support this kind of communication primitives very efficiently.
Do you think that hardware evolution will affect some of these things, some of these approaches we use, or are we kind of just too far above in a way when we talk about software to think about that, beyond like GPUs and so forth?
Oh, I mean, the hardware always, it's like the hardware impacts the software by changing the assumptions you are operating on. So there is absolutely no question that there is a lot of impact. Like for instance, obviously in many cases, this reflects in improved performance. In particular, we see a lot of still improvement in performance in terms of the communication bandwidth. Right now we can do 40 gigabits per second, seconds in a data center, which kind of changes the kind of things we can do. And it makes also running distributed computing applications more efficient. And this being said, some of the barriers still are going to remain for a long while. And like, for instance, the latency and the throughput to access, in particular, different kind of storage in the hierarchy, right? You know, accessing the GPU memory, it's at least, 10 times more throughput than accessing the RAM memory. And which again has one order or more of magnitude. It's higher throughput than accessing even a memory which is remote. So I think that we are going to have very strong constraints which are going to guide the design of the systems, and these constraints will not change anytime soon. Some of them are obviously fundamental physical limits.
Right. Mike, I was wondering if you could talk about when you start applying ML to these sort of real world problems, you run into issues and concerns about explainability, about adversarial behavior and dealing with that. I wonder how you think about those problems in the context of real world applications.
Yeah, so I think explainability is not easy. It's definitely not just finding the features that a network is using and giving them back to the user and saying, here, there's my explanation. There's often hundreds of thousands of features and they're all tangled up in some way. So part of it is, first of all, realize that you need explanations in some cases and not others. Just take human beings. If you ask me how I was able to pick up a cup, how did I move my muscles in my arm to pick up a cup? I have no idea. It's cosines and sines, and and it's quite complicated. I can't explain it. I also can't explain how I see something, right? There's a lot of the level stuff that is in somehow neural networks that is not accessible to us, and we would really want to or care to. Now you can find out if I'm an expert by asking me to do things like carry the cup with my elbow pointed up in the air, and you can learn things. You can probe me a little bit, and I can show you things that show that there's kind of meta knowledge of how I do certain things, and maybe you can even, as a scientist, learn about me that way. But I can't provide the explanation. Now, on the other hand, if I'm going to act like a doctor and give you a diagnosis of a heart disease, you're going to want an explanation from me. And it's probably not going to be just, here's my, variables I used in the neural net inside my brain. It's going to be, hey, I thought about that. I thought about the other, things that could be afflicting you, but it can't be that because this. And, I'm going to go through a chain of thinking and reasoning. And that is part of the bigger AI thing of thinking and reasoning. Just minimally think about nearest neighbor. Okay, so nearest neighbor is a deprecated technology relative to neural nets, all right? But it works damn good, right? If you take a query point and you look at k nearest neighbor, k is like 50. So you find the k points, the 50 points around your query, and you take an average of those, I bet you that would work just as well as a neural net, okay? It's gonna be, you do the neighborhood correctly. It's gonna be, neural nets are just smoothing and memorizing data, really. And that's what nearest neighbor does too. Now, why are we not using nearest neighbor? Well, hardware and software, it's really hard to do nearest neighbor. And at runtime, inference time, if you will, you have to look up all those points and you need a KD tree, and it's just not gonna scale. So that it's been deprecated for that reason, not because it didn't work. All right, now, if you're trying to do explanation, all right, showing me the local differential geometry of the neural net or the features in that region, I can't understand that. But if you show me the 50 data points nearby the query and what labels they have, and I see, oh, those points over there, we're not getting a loan, whereas these points over here, we're getting a loan, and I'm right in the middle somehow, I can sort of get an idea of how I might move towards getting the loan. So I actually think a blend and a hybrid architecture, which maybe does the neural net because it's fast at runtime, but when people want the explanation, they actually have stored some of the data and they give you some nearest neighbor, thinking style. It's not the same as the neural net, but it's probably gonna be real close and it's gonna be way more understandable. People like examples and concrete examples. In fact, in the question and answering, someone's asking me, can Professor Jordan give a concrete example, right? And that is part of the explanation story. So I think we've just been too limited. We think about one architecture, one style, and then we try to explain the black box as if that's the problem. I think that's like 5% of the problem.
Okay, we're almost out of time, gentlemen. Go ahead, Jan, go ahead.
To follow up on that, another way to achieve explainability at least for some solving some problems. It's actually to use, deep learning, the neural networks, which are obviously, like Mike said, that it's hard to explain what they're doing. It's like, it's to synthesize a solution which can actually be explainable. So for instance, if you can use to synthesize a piece of code, then if you look at the code, it's probably much easier to understand than if you look at the inputs and the output of a neural network, what it's done. The same is like you can synthesize data structures and things like that, the protocols. And so basically, fundamentally, you synthesize a set of rules. And, then when you look at rules, again, you can much easier to understand them. And in some cases, you can even prove the correctness of what you synthesized, right? For instance, of a program doing a particular thing. Yeah, so I think that's another promising approach to build and explainable or to generate explainable solutions.
All right, gentlemen, excuse me. Thank you so much for joining us today, and to the audience, sorry we couldn't get to all your questions. Thank you for joining us. Please check out the other events at this link up here, and we'll post the slides and videos very soon, and have a good day.